Okay, thank you very much. So for once, there's no equations in my talk, although I could have put some in, but I decided that I wouldn't. I'd just keep it nice and simple with lots of pretty pictures. And I'm going to take you on a journey from the very beginning of our galaxy through to the present day. And the most recent observation I'm going to show you was made last night. So it's really hot off the press as well. So if I can persuade it to change. Yeah, there we go. So our sun is at one edge of a spiral arm of our galaxy, and it formed 4.5 billion years ago or something like that. And the proto-sun area would have been rather like the Orion Nebula, a cloud of dust and gas that's contracting under the pull of gravity to form a number of protostars in that nebula. So if you imagine the birth of our solar system was in an area similar to the Orion Nebula. And if we zoom in a little bit to that proto-solar system, we've got a star or protostar at the center. Surrounding that, it's still quite hot, but that's only relative. So some of the metals, which are the silicates and so on, can actually condense, and that's what's forming the inner planets. So Earth, Mars, Venus, and Mercury. Further out, we get to an area where ices can begin to condense. And by ices, it's not just water ice, but it's ammonia, methane, and so on. And the evidence is that comets probably, by and large, started outside of that frost line. The gas giants of Jupiter and Saturn are instrumental in controlling what goes on in that forming solar system. And we're left over with some debris, what we describe as the asteroid belt. And we also have the comets that are moving around. Now, some of those asteroids have been visited by spacecraft. So we've got something of an idea of what they look like. Only the largest asteroids have enough self-gravity that they become roughly spherical. And Vesta is the classical example of that. And some of these asteroids clearly have ices as part of their makeup. However, most of the time, they don't show cometary features such as a coma, a cloud of dust and gas surrounding them, or indeed a tail. Equally, we've visited a number of comets by spacecraft, and there are some general similarities in that they're irregular shapes, often seemingly composed of two separate bodies that are glued together. And that suggests they formed in a relatively low collisional speed environment. So all collisions were gentle ones rather than being very fast, because if they were very fast, they'd have fragmented these objects. But if they can just stick together slowly, then they'll attach to each other a bit like glue. But we do know that early solar system must have been a very dynamic place. There were collisions between the asteroids and the forming planets. And indeed, some of those collisions still go on today, and I'll show you a few of those in a minute. But collisions between asteroids also take place. And there are some objects in what is today the main asteroid belt, which sprout a tail for a few months or years, and then it disappears again, and they go back to being completely ordinary objects. And probably what happens then is they've been hit by a moderate-sized lump of rock, and that has created the cometary feature. So when we look at what probably made up a comet, it's a heterogeneous mix of fragments that may have originated in different parts of the solar system. We know there's the ices and the rocky material, but clearly there is much more to it than that. As I said, the two biggest planets in our solar system, Jupiter and Saturn, very much control what goes on today. And for example, as I'll mention in a minute, comets coming from the distant reaches of the solar system, if they pass by one of these large objects, they can have their orbit dramatically changed, sometimes pushing them into an orbit that goes closer to the sun, other times moving away. And we shouldn't think of the planets being in the order that we currently see them. So if we go back to the birth of the solar system, then probably Neptune and Uranus were the other way around. And one has migrated outwards and the other has migrated inwards. And during that period of migration, it has scattered the icy objects that were in that area into distant parts of the solar system, largely forming two belts. There's the Kuiper belt, which is roughly in the plane of the solar system, and quite a number of the very longish period comets will come from that Kuiper belt. More random distribution is what's called the Oort cloud, and it's a pretty uniform spherical distribution of bodies. And to perturb those into the inner solar system needs a gravitational boost, perhaps as a star moves past at 1 light year or closer to the sun, and just give some of these objects a little nudge, but it then may take 1 million years for it to fall in towards the sun and become a comet. So the orbits of different types of object are very different. Typically, the main planets are more or less circular orbits, but as we know, Kepler decided that they were actually elliptical orbits. But the comets in particular have highly elliptical orbits, and indeed some of those may actually be completely hyperbolic, i.e. they never come back to the inner solar system. We've seen some of the evidence of cometary impacts, particularly when comet Shoemaker-Levy hit Jupiter, and it was quite fascinating to see that scar in the atmosphere of Jupiter through the Northumberland telescope. And I think, Simon, you possibly saw it through the Northumberland as well.
Saw it from home.
Yeah, but just watching Jupiter rotate and that scar swimming into view was a real surprise, because I think many people thought these are only small bits of rock or ice. Jupiter's a big planet. Will we actually see anything? Well, yes, we did. And it was truly amazing. Closer to home, we know that the moon has been hit by a number of objects. We can see those large maria, which were formed right at the birth of the solar system, when the moon was still partially molten and flood basalts could erupt and fill in the resulting crater. And we know that there's been a continual bombardment, but some of the craters are relatively unusual and perhaps indicate that comets have hit the moon in the past. Comets have always been thought of as awe-inspiring objects. They stimulate the imagination. They can be misinterpreted as omens of doom. And there is clearly a long history of observation. It's possible that an observatory like Stonehenge could have been designed for observing comets. And when you think about it, Stonehenge is in quite an odd place. It's in something of a bowl on Salisbury Plain. And so it wouldn't have had particularly good horizon surrounding it. And a hypothesis that I make, which has no evidence for in fact at all, is that possibly it was the site where a meteorite landed. And that was the indicator that they should build Stonehenge at that particular spot. Closer to home, we have our own Bronze Age features. So at Flag Fen near Peterborough, there is the remains of a Bronze Age settlement, preserved thanks to the floodwaters of the River Nen. And off the Norfolk coast, another rather strange circle where there's essentially a wooden palisade around an upturned oak tree. Now, whether that has any connection with the comet, I don't know, but you could imagine an oak tree with the sort of root bowl as being the coma of a comet and the trunk as being the tail. But a lot of these things do require a good imagination. And Chinese astronomers clearly had a very good imagination, or perhaps not, as they described a whole range of different cometary forms on some of their silk manuscripts. And each of these forms had a meaning behind it as far as the Chinese astrologers were concerned. And there was a diagram that explained what they all meant. So some, perhaps those that looked like spears, were thought to indicate war, and perhaps a bad war for the general. Others perhaps forecast a good harvest. So numbers 13 and 14 on that, a sort of well-branched cometary tail, perhaps a good harvest. And perhaps the oddest one is this one that looks a bit like a swastika or a Catherine wheel, which was named after a long-tailed pheasant. And I'm not sure I've seen a pheasant with a tail quite like that. But that had its own particular interpretation. Now, a lot of astronomers, when they saw these pictograms of comets, thought, well, no, comets really can't have four tails all pointing in different directions. However, this illustration of comet Dept in 1861 shows that comets, if you look very closely at them, can indeed perhaps not have tails, but jets of material coming out of a rotating nucleus. And it's just possible that what the Chinese had seen in the distant past was a comet passing very, very close to the Earth that was emitting active jets, and they could actually see those jets as the comet went past. The comet with the longest history of observation is Comet Halley, and this Babylonian tablet reports the arrival of the comet at its return in 87 BC. Moving on a bit, when Caesar was ruling, there was a coin issued that depicted the comet, and Shakespeare incorporated that in Julius Caesar, that when beggars die, there are no comets seen. The heavens themselves blaze forth the death of princes. And so it was only when princes died that comets were supposed to return. This perhaps just indicated that princes died quite frequently in past times. Certainly, the Bayeux Tapestry indicated the death of one prince, but the conquest of another. So here William came across and defeated Harold at the Battle of Hastings. The comet was visible at the time, and it was clearly a significant omen as far as one side was concerned. In fact, it probably was originally the better omen for Harold, because he had to fight 2 battles that year, and he won the first one. So sometimes the omens can be a bit cryptic. By the 14th century, depictions of comets were becoming a bit more realistic. And although this is often said to be a portrayal of Comet Halley, there are indications that in fact it was another somewhat brighter comet that was visible near the same time. But moving on in time, things got a little bit more outlandish. And here a comet is supposed to be portraying fire, famine, and plague. So clearly there was still something of an association in the medieval mind that comets were not necessarily good things to have. But science was still progressing, and by the 16th century, it was realized that a comet's tail always apparently seemed to point away from the sun. They didn't know why at that time, but at least they were able to do the observations and deduce what was going on. Now, very often you see what you want to see, and this applies to the whole range of sciences. It certainly applies to politics. The politicians only see what they wish to see and ignore everything else. But it does happen to what we think should be quite objective scientists. So at one time, it was thought that a comet's nucleus was a bit like a flying sandbank, and therefore it would be possible to see individual parcels of the comet. So Hevelius, when he depicted comets, showed them as having multiple nuclei in the coma. And in particular, this depiction on the left here, it was a comet that had passed by when he was only 7 years old. So I don't think he was observing that firsthand. I think he was going by the accounts of other people and just drawing what he thought they would have seen had he been there to do the observation. A similar hallucination occurred a century or so later, when people had decided that comet nuclei must be solid, but it was also thought that if they were solid, they should show phases, just like Mercury and Venus show phases, because they are closer to the sun than the Earth. So often an observer would draw what he thought ought to be seen in the way of a crescent on the comet nucleus. In reality, of course, that was totally impossible. And then as gravitational theory developed, first Newton suggested that comets might move in parabolic orbits, and he sketched out this one particular comet illustrating that orbit. And then Halley looked at the orbits of a number of comets and decided that one in particular returned roughly every 75 years. And he predicted that it would return after he had died, and he thought that history might remember him for that. And indeed, it duly did return, and history does remember Halley for being the first person to predict the return of a comet. I was lucky enough to be in Antarctica when the comet last came back, and I was the first person on the continent to actually observe and record Halley's comet from the southern skies of Antarctica. And it was quite a marvelous sight, seeing the tail, first of all, rise up a bit like a ghostly searchlight, and then the head appearing above the mountains. Other comets have appeared through the ages, and this was one of the ones that is perhaps regarded as one of the greatest comets of all time. Really bright, visible during the hours of daylight. And more importantly, it produced a really good vintage. And so some years when there's a bright comet, they are associated with a really good grape harvest and a long-standing supply of wine. Cambridge has been associated with comets, and here is an early incarnation of the Northumberland dome with its original wooden dome, and this is Donati's comet, which is thought by some to have been one of the most beautiful comets of all time, with a long, bright, curving tail. More recently, we've had one of the largest in terms of nuclear diameter comets. This is Hale-Bopp, and here seen over the second incarnation of the Northumberland dome. That wooden dome blew down in a gale many years ago and was replaced by this white painted dome. And then more recently, it's the copper-clad dome. And here again is a moderately bright comet perched above the dome. So I'm just waiting for another really bright comet to appear that I can photograph above the dome. Certainly some of these bright comets provided good observing circumstances, and you could have star parties out, everybody looking at the comet as whether it was really a means of getting people into astronomy, or whether in those days people were generally rather better educated than they are today. And so they really wanted to see what was going on. So a bit akin to some of the IOA observing evenings, where they might get 300 people coming up if it's been a well-publicized event, like two planets coming close together or something like that. But this comet in particular provided some evidence of something else. And here's a sketch of the comet made from Edinburgh. And this is the summer, 15th of July, so middle of summer. It never gets very dark. However, you can see that some of the clouds are dark, painted as dark, whereas up here at the level of the comet, clouds appear to be relatively bright. And this was the case in a couple of illustrations. And my suggestion is that these are actually noctilucent clouds, very similar to these seen over Cambridge. They form high in the atmosphere at heights of about 80 kilometers during the summer months, because that's the coldest time at that altitude. And they're supposedly first seen just after the eruption of Krakatoa. However, that sketch of Comet Kogia predates Krakatoa by about 10 years. And so my suspicion is that actually there was evidence of these clouds prior to the date. It's just that people didn't really look hard enough and describe them. And here's another set of noctilucent clouds looking over Midsummer Common, and you can see the Earth's shadow moving downwards and the lower clouds moving across the picture in a different direction. And that more or less exactly recreates the overall ambience of the pictures, the sketches from Edinburgh. Comets also feature in literature in a number of forms, not usually very credible literature, but it's nice that science fiction can produce some interesting stories. Comets are often thought to be a bit like cats. They have tails and they do their own thing. However, as we know, not all cats have tails, and a Manx cat is a tailless cat, and there are many comets that don't have tails as well. But what makes a great comet? There are basically three things that will contribute to being a great comet. And you need at least one of these, and ideally more than one. So if it passes close to the sun, it will become brighter. So the closer a comet gets to the sun, generally speaking, the brighter it is, provided that the nucleus is above a certain size. A comet that passes close to the Earth can also become prominent just through the simple inverse square law. So the closer you are to something, the brighter it is. And then finally, if a comet has a large nucleus, it doesn't need to come particularly close to the Earth or the sun to be a bright object. And Hale-Bopp was like that. It never came particularly close to either the Earth or the sun, but nevertheless was a bright object for very many months. So that it's had a very long observing period. So just looking at some of these great comets, Hyakutake was a comet that came very close to the Earth, and it had a tail stretching halfway across the sky. Now, on this particular night when I took this picture, it was cloudy in Cambridge, but it was forecast to be clear further to the west. So I drove along the A14 into Northamptonshire, and on the last junction before the M6 motorway, the clouds broke. And so I came off at the roundabout and was able to take this picture of the comet. As I said, Hale-Bopp had a very large nucleus, so it was bright for a lengthy period of time. And that period of brightness meant that a lot of people were able to see it. Hyakutake was only there for a week or so, and so a very short observing window, and that's quite often the case with a comet coming close to the Earth. But something that is distant, perhaps brightest when it's at opposition, you get a really good chance to go and see it. And then a comet that came moderately close to the sun was one discovered by Rob McNaught from Australia. And this view is from the Coton footpath behind the Cavendish, looking west in the evening twilight. And at that point, it wasn't really a terribly spectacular image, a comet. However, it then went on to be seen by a spacecraft, and this is the stereo spacecraft that is targeting the sun. Now, can I persuade this to run again only by doing this? So there it is, and you can see that as it moves through the field of view, you eventually get a whole range of striations in the tail. And then as the comet emerged into the southern hemisphere skies, those striations became readily visible. So quite a dramatic looking comet. And amazingly, those tail striations, although the comet was not visible from the northern hemisphere again, it was possible to image those striations just sticking up above the horizon. And this is very reminiscent of de Chasseau's comet of 1744, where it was portrayed as a multi-tailed comet. And you thought, well, how on earth can a comet have as many tails as that? And for some time, this was dismissed as a sort of artistic imagination of what a comet might look like. But again, the observations that are more recent have proved that this artistic image is indeed correct. So one or two other comets of the last decade or so that not necessarily spectacular, but readily visible. This Pan-STARRS comet was one that passed quite close to M31, providing some good photographic opportunities. And then the media made much of Comet Ison, which was due to become a really spectacular object visible in broad daylight. And this sequence shows it moving in towards the sun and rounding it. but that trip around the sun essentially destroyed the comet nucleus. And as it moved away, it faded a bit like the grin of the Cheshire cat until nothing was left at all. And you can see in this image several other things. You can see that the comet dives in head first, but once it's rounded the sun, it goes out tail first, just demonstrating again that those observers from the 16th century were right in saying that the comet's tail always pointed away from the sun. Another comet that was really quite nice was discovered by Terry Lovejoy. He's an amateur astronomer from Australia. And he initially found this by using a digital SLR and imaging the twilight sky, and picked out this object, which became much more spectacular as it approached the sun. And more recently, we've had a periodic comet round the sun. This is 96P Machholz, which has made several transits of the Soho field. And here we see it moving in its 2002 return, again, coming in, persuaded again, coming in head first. The bright dot near the sun with the bars going out, that's probably the planet Mercury. And then rounding the sun, but the perspective of this, we're looking at it in a flat screen, and clearly the comet didn't round the sun until some way later. And then most recently, if I can persuade this to show, I shall need to, now can I persuade this to activate without the, no. Oops, didn't mean to do that. Sorry. Take that off. That's got it. Right, so this shows it on its most recent return, again coming in head first. That's probably about its closest point, and then receding tail first. So on to observing comets, because amateur observations of comets are really quite important. The first step in observing a comet is finding it. And there is a comet in this image. I took this on with a single lens reflex camera on film, using the Thorogood telescope as a guide. So it's pointed out through the slit of the Thorogood. And you can see a trail just about, yes, there is a trail that runs across here. And just about there, the trail bisects the coma of a comet. It takes a little bit of spotting, but I can assure you that it really is there. But it also shows what Patrick Moore called Spode's law. If something can go wrong in a picture, it will. And in this case, it was an artificial satellite neatly bisecting the comet image. So a typical comet will have a fuzzy coma surrounding it. Sometimes it will have a central condensation. This isn't the comet's nucleus, which is far too small to be seen from Earth. But there is quite often in a comet a bright central area where there is very vigorous emission of dust and gas. And quite often comets will have two tails, one a slightly curved, often creamy white tail, which is a tail of dust and very small meteoric material, and that lies in the plane of the comet's orbit. And geometry may make it appear curved. It may also mean that in some cases, a tail appears to point in front of the comet rather than behind it. And then there is this gas tail, which is composed of ionized material, and that does indeed almost always point away from the sun. Now, what the comet looks like depends very much on what sort of magnification and instrument you use. So at the top, this image perhaps shows what a moderately bright comet might look like through the Northumberland telescope. The one in the middle, what the same comet might look like through perhaps a pair of large binoculars. And at the bottom, what it might look like to the naked eye. So you get a very different perspective of the object, depending on what instrument you use. The other key feature is what the background is like. And so observing Comet Halley from the pristine skies of Antarctica, where there's no light pollution, was a very different experience from observing Hale-Bopp in Cambridge, where there is an increasingly large amount of light pollution, which tends to drown out some of the fainter comets. Typically, for my observations, I use a pair of large binoculars. There's the pair of 20x80s at the observatory, but I've also got a pair in my home at the centre of Cambridge, which go with me on a few travels. And a Dobsonian telescope can be quite handy, particularly because sometimes the comet's at the zenith, sometimes it's nearly on the horizon, and the Dobsonian has that better range of altitude and azimuth, but you then do need a Dobsonian that will either give you a digital readout of where it's pointing, or you need to navigate your way around by star hopping. And at the moment, there is a comet that's visible in the evening sky. The media seem to christen this the green comet, but if you're observing it visually, there's no trace of green. But in modern digital imaging, they really do produce fantastic results. And so I've got a whole sequence of images of the comet. So here we can see the dust tail, which is spread out as quite a wide fan running in this direction, and the gas tail going up here. A little bit later on, again, the dust tail is still probably broadly in this direction. You can see that this is much more creamy in color compared to close to the comet where it's green. That green is caused by the C2 emission bands, what you call the SWAN emission bands, and they just happen to be in the green part of the spectrum. And here we have the gas tail, and you can see that there's a splitting in the tail there. That's probably what's called a disconnection event, where the direction of the magnetic field surrounding the sun changes sign, and that will detach the gas tail and allow it to drift downwind. And before in situ satellites, this was one means of measuring the speed of the solar wind. You could measure the position of these disconnections and work out how fast the solar wind was blowing. And initially, astronomers were quite skeptical that it would be sort of hundreds of kilometers a second, but that's what the evidence said. Here's another one. This was more recently after its closest approach. And we can see here the effect of perspective, because it now appears to have two dust tails pointing in different directions. But this is just the 3D geometry. The tail is actually pointing away from us in the plane of the comet's orbit, and we just happen to be looking more or less head on to that. And then the gas tail again coming off there. And finally, one from just a few days ago, this huge orange glow, that's the planet Mars. And in planar view, the comet passed quite close to Mars, but in terms of solar system geometry, there's well over 1 or 2 AU between the two objects. And at the minute, this is where the comet is. It's just to the east of Orion, with the shield of Orion, the arch of four little stars there. So fairly easy to find. It's now fading quite rapidly, so becoming harder to spot, but it's tracking in a really convenient part of the evening sky, just to the right of Orion, and so moderately easy to work out where it should be. The main problem, though, is that the observations show that it reached a peak of about 4.5, but is now fading quite rapidly. So it was 4.5 at the beginning of February. It's about 7th magnitude last night. And by the end of the month, it's going to be probably more like 8.5. So going really quite quickly. Now you can see I've put on a best fit line to the observations. This is fitted to match the naked eye observations when the comet was brightest. So these observations are made with largest telescopes. And generally speaking, a comet appears fainter in a larger telescope than it does in binoculars or with the naked eye. And I could have put the equation of this line into the talk, but I carefully refrained from doing so. But basically, there are two parameters that govern it. One is the absolute magnitude of the comet, which is how bright it would be if it was 1 AU from the Earth and 1 AU from the Sun, and how rapidly it brightens as it approaches the Sun. And we can work out the absolute magnitude of comets by the visual observations, or these days, the visual equivalent magnitude of electronic observations, and build up a picture of comet brightnesses, the absolute magnitude. And this shows a clear difference between periodic comets and parabolic comets that are coming into the solar system for the first time. Periodic ones have been perhaps around the Sun several or more times. And we can see that quite clearly, parabolic comets are on average intrinsically brighter than the periodic ones, which may be telling us a bit about the aging of comets. A few comets have been observed at numerous returns, and we can try and see if they're showing any secular behavior with time. So Comet Encke has the shortest period of any comet, so there's been a lot of returns to observe. And although that mean line suggests perhaps a slight fading with time, the error bars are such that the null hypothesis of no change is probably the one that we should stick with. Another comet, this is 59P, so this is the 59th comet to have its orbit determined and been seen to return, clearly is exhibiting a secular fading. It's systematically becoming fainter each time it returns to the vicinity of the Sun. And then finally, some comets, due to perturbations by primarily Jupiter, change their perihelion distance from return to return. And Churyumov-Gerasimenko is one that has happened to. And there is some evidence that the brightness is proportional to the solar distance. But equally, again, at the moment, the null hypothesis is one that holds. And so we need a few more returns before we can be certain whether that theory that a decrease in perihelion distance rejuvenates the comet is correct or not. Historically, many comets were discovered by visual observers, and George Alcock, who lived near Peterborough, was probably the most well-known of British comet discoverers. He made all his discoveries with a pair of binoculars, his last one through a double glazed window in his home that was specially installed so he could observe from his bedroom. Probably the day of the visual comet discoverer is over, largely thanks to some of the big professional search programs that are mostly targeting discovery of asteroids, but which will pick up comets in their searches. So Atlas is one very active search program at the moment with, I think it's now 3 half-meter telescopes scanning the sky, spread over a number of longitudes now. And Pan-STARRS, which has 2 telescopes running at the same observatory, again, scanning as much of the sky as they can. And there will be more telescopes coming online in the not too distant future. However, when we look at the sky coverage, it is by no means 100%. Most of these search programs are not covering the northernmost part of the celestial sphere. They're certainly not doing very well in the southern hemisphere. They avoid the Milky Way, which is this band here, and they don't really observe close to the sun on the horizon. So it is just conceivably possible that an amateur visual observer might pick up a comet. However, one of the things that mitigates against that is one particular spacecraft, the SOHO spacecraft, which has a couple of imaging systems on board. One is imaging the entire sky, looking at hydrogen emission. And comets, because they have a lot of water in them, that water is broken apart by the UV light from the sun to give hydrogen and oxygen, and the spacecraft will observe the hydrogen coma of the comet. And so this is the SWAN instrument on SOHO, and that has discovered a number of comets. Indeed, one was discovered in January. Amateur astronomers have followed it up. They've even computed orbits, but it's the Minor Planets Center in America that is the designated body for naming comets, and they haven't got round to giving it a name yet. It is probably going to be Comet Swan, but they do seem these days to take their time in naming comets. One interesting thing about this preliminary orbit is the distance from the Earth, 0.04 AU. That's a really close pass. So it's a bit of a shame that the timing of its return to perihelion was such that it actually missed us by quite a considerable distance. Some of the Swan comets have become quite spectacular. This is one of them, developing a fairly long gas tail. The other type of comet observed with SOHO is from the 2 coronagraphs that are scanning close to the sun, mostly looking at space weather events, where these eruptions from the sun send clouds of ionized material towards the Earth, which if they intersect with the Earth can do significant damage to spacecraft. But as a byproduct, it has discovered over, I think it's 4,700 or so comets of what are called the Kreutz group. And because the images are made freely available in near real time, amateur observers busy scanning these images. And in the early days, I was lucky enough to find half a dozen of these Kreutz group comets in the SOHO field. And we had a meeting in Paris some years ago, and some of the discoverers of SOHO comets all got together and we had our picture taken. But they're named after this chap, Heinrich Kreutz, who first linked together some of the brightest comets that passed close to the sun. And he discovered that they all had very similar orbits, and there were therefore likely to be fragments of an original very, very bright comet that might have been around a few thousand years ago. And typically they're seen after perihelion when the tail has developed to its greatest extent. Occasionally they're visible during solar eclipses, and this was a ground-based image, and that looks very similar to this SOHO Kreutz group comet. And here's another comet going into the solar field. This was a much brighter one. We can see it zooming in with a long tail. And in fact, it left its tail behind as it rounded the sun and emerged as a tailless comet on the other side. It moved into the southern sky, and I was in the southern hemisphere on December the 24th, 2011, but I was even further south than Australia. I was in the Weddell Sea, and it was 24 hours of daylight, and sadly this comet was just too faint to be visible in the daylight sky. So yeah, I've probably got a few minutes left, and it tells me I've still got 30 odd slides to go through, so I'll have to race through them. So Comet Halley was the first comet to be imaged by spacecraft, and a number have been seen since then, showing that initially we can start to map the surface of the comet, so we can start doing what might be described as geology or cometography on the surface of a comet. We can see and map the features, and we can actually target spacecraft to hit a comet. So 9P Temple was targeted to be hit. The spacecraft took detailed images, and there are plans to revisit this comet to see firsthand what the damage was done. But most of these were done during flybys, fairly distant from the comet, and so the images are relatively blurry. That contrasts with the European mission to Comet Churyumov-Gerasimenko, which actually orbited the comet and produced pin-sharp images, showing a whole range of features on the surface of the comet. Now, this is obviously a black and white image, but I think this looks very similar to this color image from Antarctica, where you have snow-clad mountains and steep cliffs, and the scenery is very reminiscent of what was seen on the surface of the comet. However, I think it will be some time before we see climbers climbing over the surface of any comet. But boldly go and all of that, I'm sure somebody will. Interestingly, the comet also shows some other terrestrial features. So here's a sinkhole, which is caused by water dissolving often soluble minerals below the ground, and the ground then collapsing. And this was one in St. Albans a few years ago, but that's very similar to some features that are seen on Comet Churyumov-Gerasimenko. Here, the collapse is probably driven by the emission of the dust and ices in jets from the comet, leaving a void beneath, which is then collapsed. And another comet that was visited shows boulders being kicked off the comet. And those boulders will form a trail in the plane of the comet. And if the Earth happens to pass through that trail, then we'll see meteors or shooting stars. This was a bright Perseid meteor that lit up the entire sky. And after the Perseid meteor shower, in ancient times, people would comment that there was a lot of this sort of green gungy stuff on the ground, and that must be the debris from the meteors. In fact, it's actually a blue-green alga called nostoc, and it is considered a delicacy in China to eat this. I wouldn't recommend eating it on any pavement corner like this, because the dogs will probably have peed on it. But if you've, in the wider countryside, come across it, it's not got much taste to it. For some meteor showers, you can predict when they'll be coming well in advance. And with the Leonids, which come from Comet Tuttle, every 33 years, the Earth goes very close to where the comet was. And so you can predict that there'll be a bright shower. And I traveled to France, the Pacific, and to Egypt to see some of these shooting stars, and also managed to see them on a flight down to Antarctica by chance. But they all seem to come from a single fixed point in the sky. So if you wanted to see some meteors coming up, the first one to see will be the Lyrid meteor shower on April the 21st. That's best seen in the early morning. And I was lucky enough to see a strong display from this particular shower in 1982 on my first voyage back from Antarctica. And coincidentally, the comet that produced the Lyrid meteors is Comet Thatcher. So there was a strong display from Thatcher in the South Atlantic in 1982. The other major meteor shower of the year are the Perseids. These will be probably best seen in the early evening because the moon interferes a bit later. But the advantage of those is they're roughly in the second week of August, and so it's nice and warm outside. Once in a while, a bigger object comes down, and this chap, Arthur Pettifer, was out weeding his onions on a beautiful spring morning and noticed his Leylandii shaking a bit and a thump in his hawthorn hedge. And he went to have a look and found a rock at the bottom of his hedge. And he picked it up and it was warm. And he thought, well, it can't be those kids then. They wouldn't bother putting a rock in the oven before throwing it in my garden. So he found the observatories and they contacted me and I went to have a look, and it was indeed a meteorite. And it was not a carbonaceous chondrite, but it was a chondritic meteorite. And prior to the Winchcombe fall, the most recent fall in the UK. But sometimes they're a bit bigger still. And one came down over Russia in 2013, blew out a few windows, caused some superficial injuries. Going back 100 years earlier, over Tunguska, an even bigger object exploded in the upper atmosphere, perhaps 5 to 10 kilometers above the surface, and flattened several hundred square kilometers of the Siberian forest. And Russia seems to have a propensity for large objects falling on it, because in the 1940s, the Sikhote-Alin meteorite fell over Russia, and that was the biggest fall of iron meteorites seen over the last century or so. But they pale into insignificance compared to the body that came down over the Gulf of Mexico 65 million years ago or so. And that certainly finished off the dinosaurs. But perhaps we shouldn't regard these objects as being entirely disastrous, because it's quite possible that comets or meteorite impacts brought Earth its atmosphere and its oceans, and perhaps even life itself. Because in those molecular clouds where there's strong ultraviolet radiation, there are the ices and dusts, that is very well a place where you can synthesize organic chemistry and come up with some very complex organic compounds, which perhaps when they arrived on Earth, added to lightning storms on that early atmosphere, created life as we know it. Some of those chemical compounds are much more like tars than anything else. And there are these tar pits in the States, which are really oily deposits, which entrapped some of the Pleistocene mammals. But that really brings me towards the end of my talk. It's time for some of you to go and have a glass of ale or two. And I'd like you to remember that dirty snowballs come in all sorts of shapes and sizes. And some of you may recognize that telescope. This is the QS Cook refractor on its old pier on the lawn by the Northumberland. And I believe the snowman is wearing a QS tie. So that brings me to an end. Thank you very much.
Thank you so much, John, for that very historical talk. Have you got any questions from the audience or on Zoom? Yes.
Yeah, I think the talk is really interesting. I was just wondering, maybe a bit of a silly question, but how do we differentiate a comet from a planet? Is there like a maximum size of chemical rotation? Then is it like a matter of just it doesn't orbit a star, or is it, you know, maybe when a comet gets to a certain size,
Right.
we consider it a planet?
So I'll repeat the question for the benefit of the Zoom audience, because I've been trained on this. So how do we distinguish between a comet and a planet? Well, comets have two characteristics. They should have a gaseous coma surrounding them, and the brighter ones at least should have a tail. So on that basis, we might decide that Mercury is a comet because it does have a sodium tail that stretches behind it. However, it isn't really composed of ices because they've all been burnt off by the sun. We could do it on the type of orbit, and certainly most of the planets are in near circular orbits. And that, to an extent, is also true for many asteroids. The eccentricity of most asteroid orbits is not that great. Whereas cometary orbits, they are definitely ranging from hyperbolic, and indeed we now have a couple of comets that are clearly from outside our solar system, because they've come in on an orbit that was unbound to the sun. So they were just moving too fast as they came in. So when the Minor Planet Center is trying to decide what to call an object, it will look at the orbit. It will look to see whether it shows any cometary features. And on occasion, it will reserve judgment. So there have been a number of objects found that are on cometary orbits, but which don't seem to show any cometary features. And the naming system has the facility to call it C/ if it's definitely a comet, or A/ if you think it might be an asteroid, but you're not 100% certain. So hopefully that gives you a bit of an answer to the question. Technically, there are some very large comets. So the Centaur object, Chiron, which is one of the objects that led to the demotion of Pluto as a planet, that clearly has a coma and has been given a parallel designation as a comet. And that is several hundred kilometers across. So technically, there's no upper limit for the size a comet could have. And maybe Planet X is a comet somewhere on the fringes of the solar system, moving inwards, and perhaps one day being discovered, and in many millennia's time, becoming the greatest comet that was ever seen. So,
Just a quick question. What's the density of the comets? Is that
right, what's the density of a comet? Most of them you could put in a tumbler of water if you had a big enough tumbler, and they would float. So a lot of them are very low density. Some of that is because they're quite often porous objects. There are a lot of voids internally. And it's that open space that gives the low density. If you just looked at the rocky part of the material, then that will probably have a density between 1 and 3. in terms of water is 1, and most silicates are about 3.
I think that's it. Thank you all for coming. We'll see you next week. And thank you, John, for that talk. I have no idea what's going on with the sound system.
Something will happen next week then. Right, good night to our Zoom audience. I will leave the system. Do I need to stop the recording or just? Oh,
Photographing comet.
have I got any tips for photographing comets? Well, that depends on how bright the comet is. So a faint comet, you definitely need to do a guided exposure. And for a really faint one, it can be quite a long exposure. But these days, lots of short exposures and stacking them is the way forward. The pictures that I've mostly taken, I've just used a few seconds with a digital camera of the more recent ones, and they do quite nicely with the bright comets, particularly with modern digital cameras. So as long as you've got it on a tripod, sometimes having a scenic background helps. So finding a nice placid lake that the comet can be reflected in, or some trees, or a distant building, that adds to the atmospheric effect. So for a couple of mine, I've used the Northumberland Dome as a good backdrop. For others, it's just what happens to be there at the time.